My name is Jason Scott. I'm an Associate Professor in the School of Chemical Engineering at the University of New South Wales. I'm also Co-Director of the Particles and Catalysis Research Group located within the school. So the project that we're working with through the CRC FFS is the manufacture of sustainable construction materials, where we look to utilise agri-waste as one of the resources to produce those materials. SME EcoMag have a process where they can extract magnesium as what's known as a hydrated magnesium carbonate from waste streams that are rich in minerals, including magnesium. And they've got a technology where they remove the magnesium and it comes out as a highly pure carbonate product. The potential exists to lock carbon dioxide up into that product. Here at UNSW, we have Natalie Aaron, who's working as a PhD student with this project.
My name is Natalie Aaron. I'm a PhD student in chemical engineering here at UNSW. I'm in the Particles and Catalysis Research Group, supervised by Jason, Scott, Rosamal, and Tam Tran, who's at our industry partner EcoMag. I started with pure chemistry, actually. I did my undergrad work at King's College London in the UK, and then I also did a master's there focused on inorganic chemistry, but then I kind of wanted to pivot to a more like engineering or material science based project for the PhD, just because I was interested in something that focused a little bit more on application. So my PhD project broadly is about developing sustainable construction materials. We've been focused on sort of like plasterboard alternatives and kind of internal cladding materials. The goal with it is to develop ultimately a carbon negative material, and we've taken a few different approaches to that. So the idea of like repurposing waste streams to flow into that, and then also capturing carbon dioxide in the material itself. So our industry partner EcoMag, they have a magnesium carbonate material that they produce, and what I do is I take that and use it to make a cementitious material that works like a plasterboard. And so there were a couple of issues that have come up with that, which is how can we integrate the carbon capture into it? There are a few approaches, but most of them you kind of still end up producing more CO2 when you look at the process as a whole than you do capturing it. So that was step one, was kind of figuring out a way that we could work the CO2 capture in there sustainably. And then the second part of that was kind of understanding how the material functions, how it hardens, and what those like fundamental chemistry principles are, because it's a pretty new material and the cementitious process is pretty complex. So it's been kind of about working out exactly what is going on in there, how do we get from A to B. And then the third part is kind of integrating additional waste materials in there to further reduce the footprint and kind of contain any CO2 emissions that are released during the hardening process. We're doing more physical testing to figure out how it performs compared to something like a traditional plasterboard. So that's looking at the compressive strength, the flammability, and also how it performs with like water. So like how it works if you expose it to really high humidity, does it lose all its integrity? And that's kind of key to how and where it could potentially be used. We actually use two types of agri-waste in this material. Normally like crop waste, things like coffee husks, rice husks, seed pods, stuff like that, things that aren't edible for us. So it's like a byproduct of food processing. So normally it's burned, but you can also do a pyrolysis reaction, which generates a biomass gas, which we use as our carbon dioxide source. And then the residue from that is a biochar, basically, which can be integrated into the material formulation as like a supplementary cementitious material, and it can affect how the material performs. So you can kind of use it to control the characteristics that you want in the final product.
In terms of the potential benefits to the construction material, the idea is that you have a sustainable construction material where you've repurposed existing waste streams and integrated them into something that has properties that are comparable to or better than existing products on the market. The benefit of the sustainable materials or repurposing waste is the idea of the circular economy, where you can take traditional waste streams, so you're no longer relying on mineral resources, extracting them from the ground, but you can take a traditional waste stream, repurpose it to produce a product that then avoids extracting minerals. It's better for the environment. If you can do it sustainably, even greater, it's a thing. And then the idea would be that I guess you still have to dispose of that, but then you might be able to take that product and look to repurpose it in some other way.